Okay, graphical processing unit or GPU is a very powerful processor that has been widely used in the recent years. The origin of this GPU is because of the graphics processing. A lot of hardware resources have been invested in single chip to do very intensive graphics processing, for example, 3D ray tracing, 3D rendering. Um, After people have been using these GPUs in graphics applications, the application domain have been broadened into other domains, especially scientific computing. So people have been investigating how to utilize GPU, the massive parallel processing capability in other applications. The basic idea of GPU is first heterogeneous execution model. So it works together with CPU or general purpose cores. We say CPU is the host and GPU is the device. So GPU functions as a coprocessor. To program the GPU, we use a C-like programming language, although there are many primitives that are specific to GPU when you write a program for the GPU. CUDA, CUDA stands for Compute Unified Device Architecture. With the CUDA, all the forms of GPU parallelism are represented in a CUDA thread. So you can think about GPU as a processor that is programmed to execute CUDA threads. The programming model is single instruction, multiple thread. We'll see in more detail in the later slides. There are many terminologies associated with the GPU, and some are very confusing. Let's try to look at some of them to understand the meaning and how architects and programmers use these concepts in their design. Threads and blocks. We say a thread is associated with each data element. So let's say you have a large number of elements in a vector or matrix. A thread is associated with each data element of them. And threads are organized into blocks, and blocks are then organized into grids. If you have the handouts that I gave out last week, there's a figure in the second page, figure 4.13. It's a kind of a example of how we organize a computation task into grids, thread blocks, and SMD threads. GPU hardware handles thread management, not the application for OS. So as we see in this figure, we have two vectors, B and C. We are trying to do a multiplication on these two, and the result put into A. Each of these vectors has 8,192 elements, and we organize them into threads. SMD thread 0, as you can see, thread 1 up to thread 15 in the thread block 0, and each thread handles 32 elements. And then these SMD threads are organized into a thread block, and altogether these 16 thread blocks make up the grid. And these are software tasks. We're looking at it from the software point of view. When this program is compiled and later executed on a GPU, the GPU has its own hardware controller to handle the thread management. So the thread SMD thread 0, SMD thread 1 could be mapped into different physical cores or stream processors in the GPUs. There are similarities between GPU and vector machines. Both are designed to work well with data parallel problems. And both have scatter and gather transfers, so you can have vectors stored in not necessarily in contiguous memory region. Also, they employ mask registers to handle conditional statements, and both of them have very large register files. However, there are notable differences as well. In GPU, there's no scalar processor, where in vector architecture there's a scalar processor for handling scalar computation. In GPU, the idea is to use multithreading to hide memory latency. In contrast, vector machines require high memory bandwidth. And also in GPU, there are many function units as opposed to very deeply pipeline units like in a vector processor. At this point, that the GPU we say has many functional units. So we call these function units as lanes, and each lane may handle one computation at the same time with all the other lanes. Here's back to the example where we multiply two vectors of length 8,192. So each vector has 8,192 elements. The overall computation, we call it as a grid, as we see again in that figure 4.13. And we use thread blocks to break down this whole computation. And we have 512 threads per block. So we divide that. So we divide 8,192 by 512. That gives you 16 thread blocks. That's why you see here we have thread block 0 and up to thread block 15. And one SIMD instruction executes 32 elements at a time. That's what you see. Here, SIMD thread 0, SIMD thread 1, each of them can handle 32 elements at a time. And block is analogous to a stripe-mined vector loop with vector length of 32. It's like you divided the whole computation into 32 elements, a chunk. And these blocks is assigned to a SIMD processor, and this multi-threaded SIMD processor is the hardware processor we refer to in the GPU. And this scheduling is done by the hardware controller called thread block scheduler. And the current generation, the Fermi architecture, has 7 to 15 multi-threaded SIMD processors. Again, some terminology. Threads of SIMD instructions. So these you can think about as the execution unit. So each thread has its own PC. And thread scheduler use scoreboarding to dispatch the instructions by resolving dependencies, also by handling the memory accesses. Now, even though there might be dependencies within a thread, there's no dependencies between threads. And this controller keeps track of up to 48 SIMD instructions. The goal is to hide memory latency, because while some of the threads may issue load instructions without waiting them to complete, without waiting the load to complete, the scheduler can schedule other threads to do the computation. As a result, memory latency is hidden. And thread block scheduler, again, we mentioned this term. Thread block scheduler is the hardware scheduler. It schedules blocks to the physical SIMD processors. Within each SIMD processor, there are 32 SIMD lanes. So each lane can handle one computation at the same time with all other lanes. And this is different from the vector processor. For a vector processor, you may have only 1 or 4 lanes, where each lane is pipeline that you can handle large throughput of computation. In GPU, it employs wide lanes, so you have 32 lanes, and each lane can do 1 computation at a time. And registers, not surprisingly, GPU has a lot of registers because of these large number of lanes. And for NVIDIA GPU, it has 32,000 registers, and they are divided into lanes. And each SMD thread is limited to 64 registers. You can have 64 vector registers of 32-bit elements, or on the other hand, 32 vector registers of 64-bit elements. So this is how you organize the registers in register files. And Fermi has 16 physical SMD lanes, each containing 2,000 registers. The instruction set of NVIDIA GPU is an abstraction of hardware instruction set. The main purpose of this abstraction is to provide capability that it can do forward compatibility. So once they have new hardware implementations, they can maintain the same ISA, so-called parallel thread execution, so that the programs compiled for this PTX instruction set can also work on the future processors. And it uses virtual registers, which will be mapped to physical registers at runtime. And the translation to machine code is performed in software. Here's an example. We have about 7 instructions, and what we're trying to do is to do a AXPY, so scalar A times vector X plus vector Y. The first 2 instructions are basically calculating the thread ID, which is coming from the block ID and block size. So with this CUDA thread ID, it can uniquely identify itself to the scheduler. Then it uses the thread ID to load data to the registers. It loads vector of I and also load vector Y. Sorry, X and Y. So with this thread ID, we can ask a thread to work on a portion of a long vector. And then the next instruction is to do multiplication on these 2 vectors. In fact, it's because this RD4 has the scalar A, but actually doing scalar multiply with a vector. Then we do the addition to get the sum of this yi and a times x. And then finally we store the result into the memory. So as you can see, the thread ID is used in all the computations to identify the elements to work on, also identify the memory locations to access. Conditional branching, we talk about these in vector architecture, which uses internal masks. GPU branch hardware also uses internal masks. It also relies on so-called stack, where we can store multiple masks based on the recent branch result. So these stacks consist of masks of each SMD lane, that is which thread commits their result. Also, GPU uses instruction markers to manage when a branch diverged into multiple execution paths. We say diverge because depends on the value or the condition that you are trying to check. Let's say if you want to do if an element is 0, you want to do statement A. Otherwise, you want to do statement B. So that's where we call the execution path diverge. The branch diverge into different execution paths. Also, this when the path converges, the stack serves as a barrier so that the threads can synchronize. It has per thread lane 1-bit predict register and specified by the program. We have example here. So the C program we want to execute on the vector is based on the value of the element. We either execute this path or this path. So this is the if branch and this is the else branch. And this what would be the assembly code implemented on this GPU architecture. First is the load instruction. We're going to use the thread ID to load that part of the vector x, and we're going to store that into this register file RD. And then we're going to compare this RD0 with value 0, and based on that we set this predict bit. This predicate bit is set to 1 if this element is not equal to 0. Okay? And based on this predicate bit, we're going to branch to this else 1. This is the label where we're going to execute the else branch. Okay? So if P1 is not set, that is if the predicate bit is a 0, we're going to branch to here. That's indication of the value is indeed 0 because we're checking this n equal here. So this else one will be this, where we can see this is trying to execute the else part of the original C statement. So what we do here is we load vector z and we assign that to this vector x by storing the value to this location. And this part is the if statement. I mean, is the true statement, the then statement here. This is to load vector y, and we do the subtraction, and it will assign the value. Okay. And both of them will converge at this point. This is the end of the if, where we will pop the original mask value. NVIDIA GPU has different kinds of memory structures. Each lane, each SIMD lane has a private section of the off-chip DRAM. It's called private memory. This is for storing stack, spilling registers, and private variables. Also, on chip, each multi-threaded SIMD processor also has local memory, and there are also memory regions shared by SIMD processor with the host CPU. Fermi architecture is the new generation from the NVIDIA GPU family. Each SIMD processor has 2 schedulers and also 2 instruction dispatch paths, and we'll see in the next slide. It has 16 SIMD lanes, and it can support 16 load store units and 4 special function units. Special function units are coprocessors for different acceleration. With these 2 instruction dispatch units, 2 threads of SIMD instructions can be scheduled every 2 clock cycles. 2 clock cycles comes from the fact that you have 16 lanes, and each MC width is 32. That means for each instruction we're gonna work on 32 elements, and because of this 16 lanes, so you're gonna take 2 cycles to complete all 32 elements. That's the 2 cycle come from. And Fermi architecture has very fast double precision computation. It employs layer 1 and layer 2 caches for the GPU memory, and it implements a 64-bit addressing mode, and also it has other features like error checking and fast context switching, as well as fast atomic instructions. This is the picture that illustrates the architecture of the Fermi multithreaded SMD processor. In each process, as you can see here, it has 2 thread schedulers and 2 dispatch paths. All the SMD lanes use this very large register file, which has 32,000 registers. And here, each SMD lane has this floating point unit and also integer unit. And we have 16 of them here and 16 of them here. In the next couple of slides, we're going to look at, in particular, loop-level parallelism. Many applications, especially high-performance computing applications, there are often the case loops used to do matrix computation or other data processing tasks. We're going to look at what kind of loops that we can make it execute in parallel, and what kind of loops has to be executed in series. And in order to figure out that, there's a very important concept. It's so-called loop carried dependence. Loop carried dependence refers to the fact that data accessed in later iterations are dependent on data values produced in the earlier iterations. Okay, that's called loop carried dependence. Let's look at this example. We have a loop. Okay, we're going to execute this loop for close to 1,000 times. And in each loop iteration, we're going to compute the sum of xi with this value s. Assume that this s is a scalar value, this vector of I. We're going to increase that each element of xi by s here. So in this case, the dependency in every iteration is not depending on the early iteration. It only depends on its current iteration. Okay? So there's no loop carried dependence in this example. In the second example, we're doing a for loop, and we're doing this loop iteration for 100 times. We have 2 statements, S1 and S2. S1, we're gonna compute the sum of A of I with C of I and put result into a I plus 1. And the second statement is we're gonna compute the sum of B of I with A of I plus 1, which is in the current iteration, and the sum is going to be assigned to B I plus 1. What we can observe here is that both S1 and S2 use values computed by S1. Okay? By that we mean this S1, the value of A in this iteration depends on the value of A in an earlier iteration. And in the second statement, the value of B of I plus 1 depends on the value of A. So that's why we say both of these 2 values depends on S1. Also in the second statement, S2 use values computed by S1 in the same iteration. Okay. So clearly there is loop carried dependence because it depends on both A and B depends on the value it calculated in the earlier iteration. The third example. Okay, we are doing this loop for 100 times. Again, we have two statements. We're going to compute value of A using its current iteration plus value of B. Okay. And in the second statement, we compute the value of B using two independent vectors. Okay. So in this case, it's S1 where we use the value computed by S2 in the previous iteration. Right? Because as you can see, we're going to use this value of B, which is calculated in a previous iteration. However, this dependency is not circular. Okay. This A depends on the B, which is calculated in the earlier iteration, but B does not depend on A. Okay. So B is independent from A and can be calculated independently, where A is not depending on itself. I'm talking about the previous iteration. It only depends on itself in its current iteration. So we can transform this kind of loop to the following one. So what we do here is we do the computation of A0 ahead of time, because as we can see, A0 equals A0 plus B0. Okay. So we can start from A of 1. Okay, so the loop is now changed to this: B I plus 1 equals C I plus DI. So that's the same as we do here. Okay, and we can rewrite the first statement into A I plus 1 equals A I plus 1 plus B I plus 1. And we change the loop ending condition to less than 100, and because we're going to calculate this B100 independently, separately. So when we look back this loop iteration, both of these two statements do not have loop carrier dependence. Okay, this B can be calculated independently. Also, A depends only on the current iteration. So this kind of loop can be made parallel. And we have another two examples. Something typo here. Let's look at this. So it's hard to figure out whether there's loop carrier dependency in a loop statement or not. One concept we leverage is the affine, which is to represent the indices of the vectors, and then we try to figure out whether a loop has loop carrier dependency by looking at this kind of representation of the indices. So we can write the indices of a vector in a loop iteration using this format: A times I plus B, where A and B are both constant number, and this I is the loop iteration variable. We assume that we're going to store the value to this location and load from a different location. So this is where this A and B and C and D are extracted from your loop statement, where the indices of the same vector, one is read and one is write. That is to say, the vector is on both left and right of the statements, and we extract this A, B, and C and D. And this I runs from a lower bound to upper bound. We say that dependence exists if both of these two conditions hold. Given I and j such that there exists j and k within this range, and also a times j plus b equals c times k plus d. This is essentially to say that you're trying to load a value for the current computation where the value is computed in earlier iterations. Dependencies generally cannot determine a compile time, but one possibility is to test the absence of dependence. The approach is to do this common greatest common divisor test. If a dependency exists, the GCD of C and A must evenly divide D minus B. Okay. So let's look at this example. We have, this is the A times I plus B. This is the C times I plus D. Okay, so in this case, the A and C are both 2. Okay? And B and D, one is 3, one is 0. So the GCD of C and A, that is 2. Okay? And D minus B, that's minus 3. Okay? And we see that in this case, GCD of A and C is not evenly divisible by D minus B. So as a result, there's no dependency in this case.
So are the dependencies being like farther during the execution time? So since they say like they cannot determine the compile time.
Yeah.
So it's only during the execution.
Well, it's hard to determine. So it's hard to determine the compile time. But with this GCD test, we can determine some of them.
No, my question was like, so when they say it cannot be determined in the compile time, does it imply that it's determined only during the execution phase?
No, I think what we want to say here is that generally it's hard to determine at the compile time. But in some cases, like if we can represent the indices using this format, and we can do this GCD test to determine a compile time, and then the compiler can optimize this to loop to assign these loop iterations into different processors. Okay, so here's an example. We have this loop iteration, and we have 4 statements in this loop. We're going to so we have vector x and y and z. And in this loop, what we are doing here is we're gonna first statement is compute y of I using x of I, and second statement is to use xi, compute xi. And then the third statement is to use y of I to compute z of I, and then the last statement is to compute y of I using y of I. If you remember that the dependencies we talked about in the very beginning of the course, we call the true dependency, anti-dependency, and naming dependency. This one, let's see, this Wi-Fi is written, right? And this Z gonna read after this Y is written. So this looks like a read after write dependency. And we have also write after read dependency, which is this one. Okay, we're going to read xi, but then next instruction is to write xi. Also, we have write after write dependency. For example, this y is written, and also this y is written. Now, we know some tricks to eliminate these kind of dependencies. Renaming is one of them. We can actually rename this several instructions, the variables of these instructions, to eliminate the dependencies. Let's say if we rename this y, and this y to t, then this write after write dependency is removed, and we still maintain the correctness of the program, right? Because this y is used as a temporary variable to hold the value of xi divided by c. It's used here and here, right? So this y is not actually depending on the value of y. Also, we can rename this x to a different name, let's say x1. Then the dependency of x is removed. This write after read dependency is removed, because the way we use this x of I is only in this current iteration. It's not a loop carried dependency. And of course, after this loop is completed, you want to rename this xi back to x for the later computation. There's another technique we can use, is called reduction. Let's look at this example. This example is actually the reduction operation. What it's trying to do is to do this vector element-wise multiplication, and then we do the summation of all the pairs, the products. So this is the reduction. We can transform this into two for loops. First, we can do this product to do the multiplication, As you can see that there's no loop carried dependence. That means this loop can be made parallel. Whereas in the earlier case, you cannot because of this sum. That's the variable you refer, which is calculated in the earlier iteration. So there's loop carried dependence. And in the next step, we can do this final summation. Okay. So when we look at this, it looks like there's loop carried dependence because this final sum is used in the later iterations. But it turns out that we can do one thing is to make this loop executed on, let's say, 10 processors, p equals to 10 here. So that is to do this summation separately, okay? And each processor is going to do the summation of 1/10 of these sum vector. And after that, we're gonna do the sum on these 10 final sum to calculate the final result.